Hi everyone, in this section we're going to look at the math behind sinusoidal transverse waves. So the vertical displacement of particles in the medium, y, it's a function of two variables, x, the position in the medium, and t, the time. So we have y at x comma t equals a, the amplitude in meters, sine of kx minus or plus omega t plus phi. So I'll show you the derivation, but I'm also going to take a minute to explain which each of these quantities mean. So we could use a cosine function here. Again, all that would change is the phase phi. Your textbook likes to use cosine for simple harmonic motion and sine for waves, so we'll go with that, but really either one is fine as long as you have the right phase constant that matches the initial conditions, and we'll get to that in a little bit. So, okay, A is amplitude in meters, we know that one. Vertical displacement y is also generally measured in meters. Then we have a new quantity here, which is k. K is the wave number, which is 2 pi over the wavelength lambda. So the units are radians per meter. And this gives a measure, a representation of the spatial period, since the spatial period is lambda. So the wave will repeat itself spatially in a period of lambda. Then we have x. Omega is the angular frequency. We know that one in radians per second still, and we still have omega equals 2 pi f. T and then plus phi, the phase constant. So first we have minus or plus here. It's written like that because the negative sign is used when the wave is moving in the positive x direction. So to the right, or whatever we've labeled as the positive x direction. And then the positive sign indicates that the wave is moving in the negative x direction, which is left. And I'll show you why. But they're switched, so that's why it's minus plus here. It doesn't matter which order you write them in, but remember that the negative sign means right motion, and then the positive sign means motion to the left. Okay, then we still have the wave speed. So the speed at which the wave propagates through the medium is still v equals lambda f. And you can see if you were to plug in lambda here, which would be 2 pi over k, and plug in f equals omega over 2 pi, you'll have v equals omega over k. So we can jump right from this formula into calculating the wave speed, or you could find the wavelength and the frequency first. Let's consider a sinusoidal wave function at t equals 0. So this wave is a snapshot of the graph that is y versus x. So I've drawn this and I have labeled on here the wavelength, the length for one cycle, so crest to crest in this case is one way to see that. So this is a general sine function. We could write a cosine function as well, but let's do sine for now. So y at x naught, which is the initial position at t equals 0, comma t equals 0, equals a sine 2 pi over the period x naught plus phi, where phi is still the phase constant. Now I've written period instead of put capital T here because they're not quite the same. Since this is a function of x, the period that goes here is the spatial period, which we know is the wavelength. So we actually want the wavelength to go there instead of the temporal period. So we have y at x naught t equals 0 is a sine 2 pi over lambda x naught plus phi. And this quantity 2 pi over lambda is the wave number k. And that's in radians per meter. So we can just rewrite it here. We have a sine kx naught plus phi. And now what I want to do is expand this to include the temporal component. Okay, to do this, I'm going to replace x naught by x minus vt. I can do this because vt is the distance that the wave will move in time t. It's speed times time, which is distance. Okay, so our function y of x at t will be the same as y at x minus vt and 0. So let's plug that in here and expand. So we have y at x and t equals a sine k. Instead of x naught, we write x minus vt plus phi. And then expanding, we have a sine kx minus k vt plus phi. And I just want to simplify this kv because we have 2 pi over lambda times vt which is 2 pi f times t. V over lambda is the frequency, and this is the same as omega t. So we end up with this wave, y at x and t equals a sine kx minus omega t plus phi. Now, when I said that this is the distance that the wave moves in time t, I was assuming it was moving to the right, and that's why we subtracted that to get back to the initial position. So this is for a right, or a wave moving in the plus x direction. So we could repeat this same derivation, and I could say x naught goes to x plus vt for a wave moving to the left. So that's why we have y at x and t equals a sine kx minus or plus omega t plus phi, and the top sign is if the wave moves to the right in the positive x direction, and the bottom sign is if the wave moves to the left or in the negative x direction. So it's a little bit counterintuitive, and we need to be careful to remember that about the signs. So it's not simple to sketch this in 3 dimensions, y, x, and t. However, we can look at snapshots of the graph either at x equals 0 or at t equals 0. So a graph of y versus x is often drawn at t equals 0, and then we have y versus x here where the period is lambda. And then here we have a graph of y versus t, and in this case it's at x equals 0, and the period would be t, what we actually call the period in time. So though these look similar, they're not exactly the same. We do have the same initial conditions since we're looking at one motion, but otherwise the parameters would vary. Example 2, a sinusoidal wave with an amplitude of 1 centimeter and a frequency of 100 hertz travels at 200 meters per second in the positive x direction. At t equals 0, the point x equals 1 meter is on a crest of a wave. Determine the values of a, v, lambda, k, f, omega, t, and phi for this wave. B, write the equation of the wave's displacement as it travels. C, draw a snapshot of the wave at t equals 0. Okay, so for part A, we're given a lot of this information. We're given that A equals 1 centimeter, and then the frequency is 100 hertz. We also have the wave speed is 200 meters per second. And from that, we can find the wavelength, that's v over f. 200 meters per second over 100 hertz, so 2 meters. And then k is 2 pi over lambda, so 2 pi over 2 meters, which is pi, radians per meter. And then we still have the angular frequency, 2 pi f. So that's 2 pi times 100 hertz. So 628 radians per second. And the period. T is 1 over the frequency, so 1 over 100 hertz gives 0.0100 seconds. Okay, in order to write the equation of the wave's displacement, we have everything we need except for the phase constant. So let's use the initial conditions to find the phase constant. At t equals 0, we were told x equals 1 meter and y is a, which was 1 centimeter. So our function here is a sine kx minus omega t plus phi. I am choosing minus because we're told that it moves in the positive x direction. So, and then we have this equal to a because it starts at the amplitude at t equals 0. So then canceling a, we have sine, I'm also going to put in t equals 0, so sine k x plus phi equals 1 when we divide by the amplitude. So in order for sine to equal 1, we have to have what's inside here, the argument, equal to pi over 2. There's only one value where this happens, so it's distinct. So we'll have kx plus phi equals pi over 2. And then we can solve for phi, so phi will be pi over 2 minus kx, and this is pi over 2 minus pi, which was k, times 1 meter. So we get negative pi over 2 radians for the phase constant. And then with that, we can just write out the full wave function. So y at x comma t equals a, which is 1 centimeter. I'll leave centimeters in there for now. Sine, and then I have pi radians per meter. This is k, x minus omega, 628 radians per second, t, minus pi over 2. So again, this is a, k, omega, and phi. Okay, and the last part, part C, is to sketch this function at t equals 0. Our initial condition we're given is actually here. Okay, so first of all, I've drawn the axes for x and y, and I've chosen to use different units for both. You can do that, so we have x in meters and y in centimeters. The amplitude is 1 centimeter, so we have that ranging from 1 to -1. And then I've marked out some points here. This is, again, as I was saying, this is the initial condition. We know that at t equals 0, this whole graph's at t equals 0. And then we have at 1 meter, y is 1 centimeter. So this is our first point that we're given instead of this one like we've been given before. So we have that. Then we also know that the wavelength is 2 meters. So we have to have a full period occurring in 2 meters. So I've drawn 2 cycles here. So knowing that, you can map out the rest because we know that we have to have half a period here before it gets to 0, so it'll have to be at a trough if it was at a crest at 1 meter. And then we can fill in the periodic cycle. So, alright, I'll attempt to sketch this in a nice smooth way here. There, and we need our, okay, that's kind of close, could be rounder here, but you get the idea. It's a sketch, so it's not a problem. This, we need our final point, since it's been 2 periods, to be back at -1, so that looks correct. Example 3, a transverse wave on a string has a wave function y at xt equals 0.12 meters, sine pi over 8 radians per meter x plus 4 pi radians per second t minus 1.12 radians. Determine the amplitude, frequency, wavelength, speed, and direction of travel of the wave. Okay, so looking at this wave function, this is the amplitude here. So A equals 0.120 meters. And then we have K is pi over 8 radians per meter, and omega 4 pi radians per second, and then that's the phase constant. We weren't asked for that, but we do know what it is. Okay, so we want amplitude. Next was frequency. Frequency is omega over 2 pi, so we'll have 4 pi, which was omega over 2 pi, so 2 hertz. And then wavelength, so K is 2 pi over lambda. So we get lambda equals 2 pi over K, 2 pi over pi over 8. So 16 meters. And then we can find the wave speed. So V equals lambda F. I'll show you here why you can use omega over K. I know I said that before, but so if we plug in for lambda, we have 2 pi over K, and then plugging in for the frequency, omega over 2 pi. So we get omega over K. So both are equivalent. Since we already have lambda and F anyway, 16 meters times 2 hertz gives 32 meters per second. And then because our function is positive here, this means that the direction of travel is left. So that's just the last part there. The function we've been using, y at x t equals a sine kx plus or minus omega t plus phi, gives the transverse displacement of the particles in the medium. So we can use it to find the transverse velocity and the transverse acceleration of the particles in the medium. To do this, we need to make use of partial derivatives. The partial derivative is a derivative of a function with respect to one variable when all other variables are held constant. Example 4, find the partial derivatives df by dx and df by dy for the function f at x and y equals 6x squared y squared plus 4xy cubed. Okay, to start we'll find the partial derivative with respect to x. So I'm going to take y to be a constant. So we'll just look at x. So the derivative of x here, we'll multiply that 2 in front and drop the exponent down. So that's 12x. The y squared is unchanged. Plus, here the derivative of x is 1, so we have 4y cubed. Okay, now doing the same with y, I'm going to treat the x squared as a constant and take the derivative with respect to y. So we'll drop the 2 down in front and reduce it to a 1. So I'll still have 12 here, but it's 12x squared y plus, now this 3 multiplies in front, 12x, and is reduced to a 2. So 12xy squared. The transverse velocity, Vy, of the particles in the medium will be the partial derivative of the displacement y with respect to time. Then the acceleration will be the second derivative of the displacement function with respect to time, so the partial derivative, or the first partial derivative of the velocity with respect to time. The partial derivatives of the wave function y at x and t with respect to time can give us the velocity and acceleration of the particles moving in the medium. So let's do that now. I'm just going to choose a rightward traveling wave, but you could do the same thing using a positive here for a leftward traveling wave. Okay, so to find the velocity, we're going to take the partial derivative of y with respect to time. So the derivative of sine is cosine, and then I'll multiply, these are constants, so I'm only interested in this term here, the negative omega in front. So negative omega a cos kx minus omega t plus phi. And then we can see here, this gives us a function for the velocity. We have a maximum speed, since cos ranges from -1 to 1, of plus or minus omega a, or the maximum velocity of the particles is plus or minus omega a, which is the same as we found in simple harmonic motion. Okay, then the acceleration of particles in the medium will be the derivative of the velocity with respect to time, or the second derivative of the position. So taking the derivative of this here, I'm going to watch carefully the negative sign. So the derivative of cos is negative sign, so we do get another negative, but then there's another negative coming when we multiply this out, so we are left with a negative overall. Negative omega squared a sine kx minus omega t plus phi. Okay, so this gives the acceleration at any time t, but we can see that the maximum acceleration will be plus or minus omega squared a. Also in general, as with simple harmonic motion, if we compare the functions here, this is x. So we end up with the acceleration is negative omega squared x at any point. And just remember that this speed is the speed of the particles in the medium. It's different than the wave speed. Wave speed is still given by v equals lambda f for the constant wave speed. Okay, I also wanted to mention that when we're given initial conditions and not the amplitude, we can find the amplitude by using this equation here. So our y at t equals 0, x equals 0 squared plus vy at 0, 0 squared over omega squared, and the root of that. So that will give us the amplitude, and you can try deriving this if you'd like. I'm not going to do it because it's the same as when I did this in simple harmonic motion, so we end up with the same relationship here. Okay, example 5, a transverse sinusoidal wave on a string has t equals 25 milliseconds and travels in the positive x direction with a speed of 30 meters per second. At t equals 0, an element of the string at x equals 0 has a transverse position of 2 centimeters and is traveling downwards with a speed of 2 meters per second. A, what is the amplitude of the wave and phase angle? B, what is the maximum transverse velocity? C, write the wave function for the wave. Okay, so I've listed the given information here, the period that it's moving in the positive x direction, the wave speed, y at 0, 0 is 2 centimeters or 0.02 meters, and vy at 0, 0 is negative 2 meters per second. Then we can quickly find omega. We're going to need that, so 2 pi over the period. 2 pi over 0.025 seconds gives 251.3 radians per second. Okay, so for part A, we want the amplitude and then the phase angle. So finding the amplitude first using the relationship I just showed, we have the root of 0.02 meters squared plus negative 2 over 251.3 squared, and that gives 0.0215 meters for the amplitude. To find the phase angle, we can do this very similar to how we did in simple harmonic motion. So what we want to do is use the initial conditions here. So we know our function is of the form y at x and t equals a sine kx minus omega t plus phi, again negative here because it's moving in the positive x direction. And then that means that y at 0, 0 equals a sine phi, putting both x and t to 0, and we want that to equal 0.02 meters. So we can solve for phi here. Phi will equal sine inverse of 0.02 meters over a, 0.0215 meters. And make sure your calculator is in radians, and you should get 1.19 radians. Now this is the solution, but there are often cases where we're not sure, because remember there are two angles that correspond to each sine value. So we want to check both, and we're going to do that with the sine of the velocity. So we do need to do a check. Remember the cast rule here. So this is about somewhere on this side, 1.19 radians. That means sine is positive in both upper quadrants. So we also have 1.19 radians over here, which is pi minus 1.19 radians, or what is that, 1.95 radians. Okay, so let's check both. When we do this, we can look at the velocities. So taking the derivative, Vy at x and t, as we just did, is negative omega a cos kx minus omega t plus phi. So the initial velocity at 0, 0 is negative omega a cos phi. So let's try each one. If we try 1.19 radians, we'll have negative omega a cos 1.19. This is in this quadrant where cosine is positive. You can use your calculator, but we can also just see that here, that it's going to be positive, which gives an overall negative velocity, and that's what we want. We want negative 2 meters per second. Okay, so then we can try negative omega a cos of 1.95 radians, and that's going to be negative since only sine is positive in that quadrant, and again you can just check in your calculator if you want to. So this gives an overall positive velocity, which isn't right. So we know that this was the correct phase angle that we wanted there, but make sure to do the check, because in the case that the sign was wrong for the velocity, we would have chosen the other angle. Okay, now part B, we want the maximum transverse velocity. We know it goes between plus and minus omega A, so the maximum is omega A, at least the maximum magnitude is that as well. So we have 251.3 radians per second times 0.0215 meters, which gives 5.4 meters per second. Okay, and then part C, we're asked to write out the function for the wave. So to do this, we're going to need k, and we have everything else that we need to put into that wave equation. So let's find the wavelength first. It's v over f, both of which we have. So this is also, since we have the period, we can just do speed times the period. And that's the wave speed, which is 30 meters per second. And then the period was 0.025 seconds. So we have 0.75 meters for the wavelength. And then k is 2 pi over lambda. So 2 pi over 0.75 meters gives 8.38 radians per meter. And that's really the work done. Now we'll just write it all into that wave equation. So we have y at x and t equals a 0.0215 meters sine k 8.38 radians per meter x minus omega 251.3 radians per second t, and then plus phi, which is plus 1.19 radians for the phase constant. And we're done. That's it for Module 2.2, so please let me know if you have any questions, and next we'll look further into the speed of waves.